So good afternoon, everyone. Thank you very much for coming to this CircularChem showcase. So it's the first time we have this center-wide showcase. So some of you might think we have a lot of events already, but the fact is our first showcase ever from the center. My name is Xuan. I am the PI and director of the center. So before we get started, just very simple housekeeping. There won't be any test alarm this afternoon, so if there's an alarm, it will be a real one. So please exit the building through the nearest exit. I think that will be on the back of the building, and do not enter the building until the alarm is stopped. And if you haven't completed the survey, please do follow the QR code to complete the survey. So, as I said, it's been really great to see many of you here at Loughborough University. I mean, this showcase is designed to basically to present what has been done throughout the 2 years of the center. I see many familiar faces here, but also some new faces, which is fantastic. Thank you for all your great support through the 2-year journey of the center, and we are really looking forward to develop new collaborations with some of you. For those of you who are not familiar with the center, the full name of our center is, let me try if I can get it right for one time. It's UKRI Interdisciplinary Center for Circular Chemical Economy. Yes, I think that it is. So it's been part of the UK government's strategic environment under the NICER program. So it's a national interdisciplinary program for circular economy research. And under that program, there are 5 centers looking at different resources flow around chemicals, definitely our center, but also other centers look at metals, textiles, construction materials, and the overall aim of the program is to build circular economy for the UK industry. And we are very happy that the government and EPSRC realize chemical sector is probably one of the most important ones, and we get the funding under that scheme. And as I said, it has been 2 years, so there's a lot of research output and early impact throughout different research groups of the center. So that will be presented in the 3 days event starting from today. So in this afternoon, you will hear more about the enabling technology side of the progress, which is led by Professor Alex Cohen here. And tomorrow we will more shift towards the system thinking, life cycle analysis, which Benoit is leading from Imperial College, and then on the third day we're more shifting towards the policy, social science, business model. So you will see the evolvement of the topics of the 3-day event. Okay, so I think that's all I want to say, and again, welcome to the event. I hope you find it interesting, inspiring, and useful. And I also hope it can be kind of a networking event because, as I said, this is probably the first center-wide showcase event after two years or after the COVID. I hope it, of course, we want to talk to you, but we also want you to talk to each other, maybe just to establish some new connections and networking opportunities. Okay, so let's move on to our first speaker. So that will be Professor Chris Slootweg from University of Amsterdam. So thank you for coming. I know you have a very tight schedule. You have to fly back tonight. Still, thank you for coming, even during such tight schedule. So Chris has been very well known for his concept or principle of circular chemistry, which I believe we will hear a little bit more. So I think the circular chemistry principle is all about optimizing and sustaining the linear process and see how we can move beyond value extraction and aiming at making chemical processes and production cycles to be more circular, and how we can use opportunities using waste or ideally products as resource. So by reading at the abstract, I think there's a lot of similarities, but also I think some sort of different ideas or different interpretation of circular economy around chemistry. So that's really great to hear what others are doing outside the UK and the other part of the world. And I'm very happy, and I'm very, very interested to talk to Chris afterwards. But without further ado, Chris, thank you again. And I will move on to, yes, thank you, Chris. Yeah.
Thanks a lot for the kind introduction and very kind invitation. Yeah, it's wonderful to be here, and as indicated, apologies for flooding in the country and out of the country on the same day, but I hope to make up for that with some of the circular thinking that we have been developing in Amsterdam. So, as a start, a shout out to the Ellen MacArthur Foundation, who, like 2 weeks before the climate conference in Egypt, published this picture. So it's focusing on renewable energy, but it highlights that ambition, that realization is only half of the story and can only succeed if we complement the picture with the circular economy. And so any new trend, any transition can only work well, in my view, if we do it circular, and if we fully abandon our linear thinking. So, shout out to my group. It's very fun and rewarding to work with them, and also highlight for some of the funding agencies that allow us to have fun and develop circular concepts in Amsterdam. I should say I'm quite humbled to be an Humboldtian, not in the first place or not in the last place, that he, as a scientist, highlighted the impact of mankind on planet Earth. So the sustainable thinking actually started with Alexander von Humboldt. And he published books, inspired Charles Darwin, and Charles Darwin afterwards wrote The Origin of Species, which was also maybe due to Humboldt and his pioneering events. So let's start here. Think back a few years, maybe a few more years, thinking of early Earth, where, as I mentioned, Charles Darwin basically developed the concept of thinking in terms of the soup, where life originated, where the 6 key elements came together, so carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, and life originated. And so these 6 key biogenic elements are still essential for sustaining life on planet Earth. But my proposition is that these exact same 6 key biogenic elements are now the origin of waste, indicated in this cartoon. So if we look at the big 2 waves that are upcoming, I think it's all our ambition to make sure we basically flatten the curve and prevent this from happening. Now, a more scientific picture, perhaps, is this one. Are you familiar with the planetary boundaries concept? Yeah. So this is, planet Earth, traffic lights, color coding, and at the outset there is, I would call them global waste problems. And so on top, climate change, ozone depletion is again in the green, so that's good. At the bottom, basically, waste problems due to the excess use of nutrients. And typically, many of these are interconnected. And so systems thinking was addressed already. And so CO2 in the air, CO2 in water. And so many of these concepts, many of these waste problems are interrelated. But if we look at the molecules behind, quite a few of these large global waste problems actually concern very simple molecules, consisting actually of the elements that I just highlighted are based on carbon, hydrogen, oxygen, phosphorus, nitrogen, and sulfur is actually coming from oil refinery, linked here, and used abundantly as sulfuric acid in the production of phosphorus-based fertilizers. Now, at the time, 2015, the novel entities, so basically chemicals, human-made chemicals, were not quantified. But since last year, this has been quantified as well, and it's not looking pretty either. So this is full in the red, which basically gives us a clear opportunity to develop chemistry which does not basically link to these waste problems, but we basically try to solve them. Right, so it's always nice to highlight challenges to make it more clear. Pictures always help too. So this is the Dutch view on the nitrogen problem. This is basically a satellite image. I'm sure there is data for the UK as well, but this is the picture I can share now. So this focuses on nitrogen oxides. Basically, industry is indicated over here. Anything at high temperature, combustion, Rotterdam area, Antwerp area, the Ruhrgebiet. So clear nitrogen oxides visible. And on the right, this is ammonia. Basically, pee and poo of animals indicated here on this picture. So in the Netherlands, we've got quite a few millions of chicken, and they live in Barneveld, that's over here. And we get millions and millions of pigs, and they live over here. So that's clearly indicated by this picture. But this is only what's in the air concerning nitrogen. And if we think of what's in our waterways, concerning nutrients in general, ammonia, nitrates, phosphates, then the picture is like this. So once the fertilizer over there, if it comes in our waterways, it remains a fertilizer and basically fertilizes the oceans. Now, we know these problems for quite a while. And so 2 weeks ago, this was indicated again now in the Observer. And the article highlights the upcoming shortage of the materials that are coming from the mine, phosphate in particular, but it at the same time highlights the acute waste issue, which is also in this picture clearly visible. Now we know about these waste problems for quite a while. So on the left, it's an article highlighting the disturbance of the phosphorus cycle in nature, published of course, in Nature. And so this is 1944. This is a newspaper article from 1912 that highlights the direct link between coal, CO2, and climate change. And if I look at, for example, 2 years ago, Nobel Prize in Physics, these two gentlemen basically worked for 40, maybe even 50 years for developing models to highlight that you can actually predict and quantify and qualify climate change and then couple it to CO2 emissions. So 40, 50 years to highlight that we have a problem, at least that CO2 emissions are increasing. And we don't have, if we think of our ambitions 2030, 2040, 2050, we need to develop the solutions much faster. So the only solution I can come up with is illustrated with this quote. So we need truly radical change, converting a linear economy in a circular economy, and as such, not only thinking in terms of resources, but ideally influence and implement much more this circular thinking. Now, from a chemistry viewpoint, the green chemistry principles have been, phenomenal, have huge impact in academia and industry. And so it's now 25 years that these principles have been published. And in the Netherlands, these also have been implemented at high school chemistry textbooks. And so the use of these principles is spreading. And we started to think, are these principles enough? Are they suitable to actually also develop this circular thinking, the circular economy? And one aspect struck me, because I once attended a talk, and there was a student who went to, did basically a research project, and he said, well, if I replace ethanol for bioethanol, then my entire process is green. And I was like, can you quantify that? Because, I mean, if you change a resource, from oil to CO2 to biomass, it's changing a feedstock. But can we at the same time also quantify the sustainability impacts? And that's, of course, a completely different game, which needs to be done as well. But if we only change the feedstock, make the same product, then not necessarily we also solve the waste problems connecting to the product. So here is this, I would say, circular thinking really important, where we design products that actually can circulate quite easily. So by teaching green chemistry and discussing what is a circular economy with our students, I actually came to the conclusion that the green chemistry principles are really good, but they optimize linear processes. And obviously there are many papers behind the concept highlighting all the different aspects, but if you simply look at these 12, it optimizes the linear economy. And if you look at the electrification of the chemical industry, that's probably the last step, the last optimization step of improving our resources to product way of thinking. But if we want to develop the circular economy, and then obviously this is utopia, but it's good to start thinking and discussing how can we actually develop chemistry towards this ambition. And the linear economy isn't looking too much different, except recovery is added and recycling is added, and both need to be working together, and so that whatever is recovered is actually suited for recycling. So if this is the linear economy, then at the end waste is the result which we do need to use as resource. But the circular thinking, the circular economy, actually, if you think of how it actually works, is, typically I take a plastic bottle, but this is also a nice example. It doesn't really matter if we make this from biomass, CO2 or oil. It's designed to be reused. So the next cycle, number 2, 3, 4, and so on, this is the product, is the starting point for the next cycle. And so in terms of chemistry, if we start to focus much more on the product, because the product needs to be renewable for the next cycle, then we can also design the product such that actually it can be circulated. So I think it was now 5 years ago in my green chemistry, it's now called green and circular chemistry class. But I typically have an essay assignment, so I asked the students write down the 12 principles of circular chemistry. And they looked at me a bit funny because they didn't exist at the time. And then I said, yeah, okay, I can share knowledge and you can reproduce it, but that's not very exciting. Create something, some new knowledge. So they did that, and with the 2 best students, we actually put the things together, and at the end we published it as well. And we thought this might be a good way of starting this circular thinking also from a chemistry viewpoint. Now, I mean, here is highlighted maximize atom circulation. So how can you efficiently reuse atoms? For example, the design, I would say number 7 is the most important principle. How can we truly design chemical products, materials, molecules that can be efficiently recycled or reused? And obviously, the sustainability needs to be assessed, not just qualitatively, also quantitatively. And number 10 is actually interesting, because the linear economy is designed to sell products. But if you say, I mean, there was somebody a few years ago who went to Philips and said, I don't want to buy any light bulbs, I just want to have light. Please give me a contract, I'll sign it, and then give me light. And then suddenly for Philips it's not rewarding to design light bulbs that needs to be replaced every year. And suddenly it's actually rewarding to design the product much more sustainably and also recycle it. It's actually, maybe not for every product, but for many, selling a surface can be rewarding and definitely sustaining the chemicals. Reject lock-in. If you think of the 600 fossil fuel lobbyists that may be in Egypt at the climate conference, whereas we should, of course, promote the new chemistry that also offers the solutions. I think, also as part of this 3-day event, we really need to unify academia and industry and also provide a coherent policy framework that offers the solutions. So let's focus on developing the solutions. And for now, in my lecture, I will focus on 3 aspects that we work on in Amsterdam. So CO2, ethane, key greenhouse gases. There are basically 2 approaches. You can use it as resource. So that will be also discussed, if I'm right, in the next session. And I will focus a bit on how can we avoid CO2 emissions, and I'm focusing on energy carriers that basically contain no carbon at all. The other is the design in chemistry, which is quite interesting. If we not only focus on function, but also on recyclability and the properties in relation to human health and the environment. But first, let's have a look at the nutrients. Because typically this is highlighted as a problem, but now let's flip it around. Let's look at this from as a solution. It's an opportunity to create renewable ammonia. It's an opportunity to create renewable phosphate, which can actually be quite handy, especially if there are places where there is no phosphate mine and when there is no Haber wash plant. Because using this as resources is, I think, a big step forward in avoiding the problem in the first place. So I'll focus on phosphorus. Why phosphorus? Isaac Asimov already said of the 6 key biogenic elements, phosphorus is limiting because there is simply no substitute nor replacement. So it's clearly life's bottleneck. So we should be in particular careful about phosphorus, but of course the circular thinking should be applied to every chemical element in the periodic table. Who is this? Anyone? Anyone know who this is? It's Hennig Brandt, and it's an alchemist, and he was looking for the philosopher's stone. And so anything that can convert lead into gold, or cheap metals into precious metals. And I really like this painting. for numerous reasons. I mean, not only the discovery of an element which doesn't exist in nature is rewarding. The experiment that Henrik Brandt performed is quite interesting as well. Because he was quite desperate, right? He was looking for the philosopher's stone, and he was boiling down liters and liters of urine, hundreds of liters, in the presence of carbon and sand in this flask, and found phosphorus. And phosphorus easily burns in the air. That's visible over here. And the phosphorus-oxygen bond is very strong, hence it burns easily. And that's why also nature adapted this as a, also in our body as an energy system. What I like also here is that Henrik Brandt basically started the whole phosphorus chemical industry with this experiment using a renewable resource. But for some reason, society did not want to scale up this process, which is clearly too bad, because we went for the mines. So this is one in Morocco. It's owned by OCP, and this is a human being. So clearly, there is enough in the EU or Europe. Not sure what to say, but close to home, there aren't any phosphate mines, apart from one small one in Finland, which runs out in 30 years and can only supply 10% of our demand. So there is enough, but maybe in 300 years there isn't anymore, and there is a geopolitical dependency, which is at the moment okay, but you never know what happens in the future. But we use this in a linear fashion, creating lots of green chemistry. And so this is the problem already. And so whereas we should develop solutions to prevent or to optimize our local phosphorus economy, this is the problem already, also indicated by the planetary boundaries concept. So the solution is actually recovery recycling. And we close the loop, then we use this as an opportunity. We create local resources that we then also can locally convert into products. Now, inspired by what Henrik Brandt did centuries ago, we thought, how can we recover phosphate? How can we maybe at the same time recover ammonia? And both of these are soluble in water. So what can you do? I mean, as a chemist, you can throw in elements. And if you find the right combination, adding, for example, magnesium chloride, magnesium oxide, then in this case, struvite is formed, and struvite is insoluble in water, precipitates, basically recovering phosphate and ammonia at the same time. So this is pretty neat. And in the Netherlands, this is done at 20 kiloton annually. So this is starting to become really interesting. The quality actually is superior over what comes from the phosphate mine. Doesn't contain any uranium, any cadmium. And so this is ready for use as a renewable resource. But the technology was lacking. So that's what we started to develop. But first we showcased this concept at the Lowlands Musical Festival. It's like Glastonbury. So it was in 2019. And we demonstrated circular chemistry at the festival. We had the best toilets close to the main stage. And it was kind of fun. We also had a survey. It's like, please tell me what could be in your what could end up in our struvite, basically. And then we have a full analysis of drug metabolites and so on and so forth up to the nanogram level. And this is still suitable for recycling. So in terms of circularity, we took a showcase, probably the worst place to recycle phosphate, but still it was good enough, apart from being fun. and we highlighted that this can be reused. But of course you need the technology to do so. So what we developed is basically the production of, for example, monoammonium phosphate. That's a high-quality fertilizer. It's also a flame retardant. And the ammonia now comes from Haber-Bosch. The phosphate in the product that you can buy on the market comes from the mine. But in this case, both of them come from Slootweg, and the magnesium needed for this cycle can both go back to the wastewater treatment plant. And so this is actually quite rewarding. Slootweg may be the easiest phosphate, renewable phosphate that can be used. And there are other sources like sewage sludge ash, and also those can be used in our process. So currently, or this is actually already 2 years ago, the Sesfos, the company we founded, runs a pilot, like a batch at 50 kilograms, and also a continuous process at 500 kilograms an hour is now running. And basically, the company is now full on the way to starting to develop a circular phosphate industry, and is now has this ambitious plan to go to a 2 kiloton scale in the coming years. So let's see how things develop. It was really rewarding that 4 to 5 years ago we started with a few milligrams, and now the chemistry already runs at a larger scale. Purely showcasing the concepts that we developed in the lab, and also for the students in my lab. This is fun to see this developing. Right. Let's have a look up here. So, like I said, obviously both of them need to be used as resource. Let's now focus on how we can avoid these two emissions. And for that, it's always good to know what the current state of the art is, or current state of the affairs maybe, because CO2 comes from everywhere, and we can and should close the CO2 or carbon loop for the industry, producing chemicals, producing cement. We should do the same for iron and steel production, for our transport sector, aviation, 2%, energy use in buildings. And so in many sectors, many industries, many of these produce enormous amounts of CO2, and all of that has to go to zero. So that is a challenge, but we cannot do everything at the same time, but we can develop the concepts and the vision that actually ultimately should realize these solutions. So the Paris Agreement is quite clear, allowing 1.5 degree warm up, 2 degrees maybe, not as a target, but really as the worst case scenario. That's where the models end up, and they show a rather radical change. And so this is one example of the radical change that I was illustrating before. So the only way to do this is we need to decarbonize our energy system. Okay, emissions go up, but we need to go down, and ultimately we usually need to go to negative emissions. And so if you look at the energy sector, I think this is also requires a large focus point. Maybe a sixth center of circularity can focus on the energy sector. And so how can we do this? So this picture actually I really like because it highlights green electricity production, and solar, wind, maybe we need nuclear in the mix. It highlights energy storage, if you think of batteries. And then when do you need hydrogen? Because in this picture, if the energy storage, the electrons directly is not suited for the use case, then hydrogen comes in. But of course, once you produce it, you also may want to store it in one way or the other. So let's look at hydrogen in a bit more detail. So this picture I quite like, because hydrogen has been promoted as the solution for everything. But clearly, if we focus on the details, this is not the case. It will be an essential component of our new energy system. So if we produce the green electrons and use them directly in a battery, using the battery, whatever car this is, it works beautifully. But mind you, like 60 liters of gasoline is now 600 kilos of battery pack. But for a car, this functions. Or we can go for the same amount of electricity, then hydrogen production, and then from hydrogen back to green electrons using a fuel cell. So 2 extra steps work beautifully as well, but then due to these 2 extra steps, the efficiency is simply lower. And so for a car, using the electricity directly seems like a good approach. For trucks, this is also upcoming. Still, for me, a crazy idea, but these prototypes are there, and there are even reports. So TNO is a Dutch research institute will highlight that in 10 years' time, the electric trucks will not only be cost competitive, but also more efficient in terms of energy use. And so for trucks, buses, maybe not the very large heavy-duty trucks, but for many of our public sector or of our transport sector can be electrified. And then, of course, we need to develop the infrastructure, but in terms of efficiency, this seems to be the way to go. So where is hydrogen then needed? So I'll use this scheme from Michael Libri, and there they highlight hydrogen. We clearly will always need to produce ammonia, unless we have a closed-loop ammonia system where everything is recycled. We always use it needed for hydrogenation, hydrocracking, currently of oil, in the future maybe of plastic waste and so on. Desulfurization is connected to oil. Maybe we don't need that in 50 years' time anymore. And then at the bottom, that's clearly the regime where we can directly use electricity. Think of light aviation, trucks, cars, domestic heating, power system balancing. According to this scheme, this can be all electrified. And then there is this middle regime, where biomass, biogas is a suitable solution. But you can also wonder in the long term if we should avoid the CO2 footprint. Even if it's CO2 neutral, it's still, upon using it, has emissions. So if we should focus on this, or it should be only hydrogen and only for electricity. So currently we have a demand for hydrogen, which is substantial. It's 94 million tons per year. But currently it has an even more substantial CO2 footprint. So in terms of our hydrogen usage, the first ambition should be to fully decarbonize the current hydrogen production. At scale, that's a substantial effort, but that's definitely the first thing to do. And second, we clearly need more hydrogen, and clearly we need more clean hydrogen. And so from methane to hydrogen, how to deal with the CO2, can we fully go to water electrolysis, for example. So, like half a year ago, this report was published by these two, and they highlighted that 60% of clean energy, clean hydrogen, I should say, will be transported over long distances in 2050. But any idea what the reason for that is?
Solar.
Yeah, exactly. If we think of the UK, Amsterdam, I mean, clearly the sun shines always here, so it will be also always much cheaper to produce hydrogen here. And if I look at the current plans for the hydrogen infrastructure in the Netherlands, then the electrolyzer capacity is not even enough to supply all the hydrogen that Tata Steel requires in the Netherlands. So there will be always a need for more hydrogen, and if this can be cheaply produced elsewhere, that offers a business case to get it to Europe, to the UK, and that should be competitive, obviously, with the local production. So I work in Amsterdam, so Amsterdam is a lovely place to visit, I guess, but it has an ambition in terms of the energy transition, because now it's still a fossil fuel hub. So all these thingies here are filled with fossil fuel, and the Port of Amsterdam has the ambition to become a hydrogen hub. And how to do that in a densely populated area? That's not so easy. And to have storage for gaseous hydrogen, no way. Ammonia as a hydrogen carrier, no way. Port of Amsterdam says no. So how to do this safely? Of course, pipelines. Pipelines is probably the easiest way of transporting large amounts of hydrogen, but many of the needed pipelines are currently not in place. So this is the target, so how to get the hydrogen here, and this should be done safely. So when there are no pipelines yet, how to carry, how to store the hydrogen and transport it. So this scheme I actually quite like, because this is the benchmark, our current regime, and these are actually options how to transport the hydrogen from, for example, Qatar, from Australia to the UK, to Amsterdam. So one option is to liquefy hydrogen 20 degrees above the absolute minimum. So companies work on this for good reasons, but for long-term storage, for very long distances, this seems challenging. So what's the alternative? Ammonia, obviously. Port of Rotterdam fully goes for ammonia, but like I said, for Amsterdam, ammonia is part of the nitrogen problem. So we cannot dispose it, obviously, but its toxicity is the reason that Amsterdam says no. So then these are actually two interesting alternatives to explore in a bit more detail. So that's also what my group is focusing on. Can we design efficient organic carriers for hydrogen uptake and release? And can we design efficient solid inorganic hydrogen carriers for uptake and release? So, and then the dream scenario is that the boat sails on hydrogen and also carries lots of hydrogen in the form of either the liquid or the solid carriers. Now, interestingly, sodium borohydride, as one of the options in this case, is still currently produced linearly. And so it comes from borax, from the mine. Herbert Brown got the Nobel Prize in 1979 for his boron chemistry, and he invented the current industrial production of sodium borohydride, but it's still linear. And so to be able to use it as a hydrogen carrier, we need to develop the chemistry so that it actually can be used in a circular fashion. So our concept, we start with sodium borohydride, 4 atoms of hydrogen, 4 hydrogen atoms, and then adding water, then 4 molecules of the hydrogen are released. So that's actually quite interesting, because the energy density is already reasonable, and the output is even doubled. So if you only use a small amount of hydrogen carrier, then this is packed with water. We'll see here a water displacement reaction, where the hydrogen gas basically pushes the water to the next vessel. So the release is at room temperature quite rapid. Whereas many of the, let's say, competitors, ammonia, you need 400 to 500 degrees of the current state of the art. Liquid organic carriers also need 200-300 degrees. This can be done at room temperature, which could be useful for regions where electricity price is high, and where you don't want to put extra energy in the system to release the hydrogen. Now, crucial part, of course, is to recycle the carrier, and this is what we're working hard on at the moment. And currently we have a cycle for hydrogen release and recycling that also connects to the industrial production of sodium borohydride. So the second step is already at technology readiness level 9. The Port of Amsterdam, like I said, they want a hydrogen import, export facility. So they're currently constructing this boat, and the boat actually runs on the concept of sodium borohydride hydrogen production on board, and that actually in a fuel cell the electricity is needed to propel the ship. So it's actually quite fun. I mean, if this will fly, this concept, who knows? But at least there will be one prototype that will demonstrate it. Now, the use of sodium hydride was never circular, was never intended to be circular, but we redesigned the chemistry to be able to do so. And this design element is something that I really like, and I think we should fully focus on every single molecule of material in much more detail. The concept is already well established, as such, adopted by industry, but how to do this, that's still lacking. And so the academic thinking, the industry adaptation, and how to do safe and sustainable by design, it's really in its infancy. And so that's why also this I like to develop in a bit more detail. So if we focus on the molecules and materials and thinking in terms of cycles, then basically this is option 1. So design products for recycling. Think of plastics, think of large streams, but there will be many molecules and materials that are not intended for recycling. So think, for example, pharmaceuticals, think of pesticides if you want them to use or not, personal care products. You know, from the sewage, we cannot recollect and recover every single medicine, even if we would want to. So these need to be designed for full degradability, in harmony with the techniques at wastewater treatment plants, perhaps. But this is really the balance. Can we design for recycling or reuse, or at least we have to focus on eliminating any possible negative side effects. Because, for example, producing clean water is becoming a serious issue at the moment. Because all these pharmaceuticals, more and more are persistent, more and more are persisting in our even in our clean water. So that's something we need to avoid, and we can do that by better design. So as a showcase, let's focus on the design of organophosphates, because some of them are used as flame retardants, and at the same time they're also detected in the environment. So for us it was an interesting use case to see if we can develop things in a bit more detail. So I mentioned closing the phosphorus loop already. So solving the phosphorus problem, it's the top 2. So we need to shift from phosphate rock to phosphate waste, basically. 90 to 95% of the usage is in fertilizers and animal feed and food additives. So the Netherlands, for example, imports more P in food, soybeans and so on, than P in fertilizer. But both are key components to close the loop. But for chemistry, this is a challenge. But this is only 5 to 7% of the problem, but still it needs to be solved. So if we currently look at the production of flame retardants, organophosphate based, then this is the synthesis. Phosphate rock goes fully to the element, like Hennig Brandt illustrated. Then it's chlorinated, it's oxidized, and then it's substituted, so chlorine, chloride for any group. So it's a multi-step process, and it includes basically a P refining identical to steam production. So first from the oxidation state 5, we go to 0 over here, and then the product is back at 5. So it works, it's implemented in industry, but you can guess we should be able to improve this, right? So can we avoid the electric arc furnace for the production of elemental phosphorus and basically use these straight away in the production? And this could or should be possible because there are reports that highlight that struvite, one of the renewable P sources, could actually be the mineral at early life responsible for the organophosphate production. But currently there is no synthesis whatsoever reported that showcases this, so that's what we're trying to develop. And so there is clear hope for converting inorganic phosphate to organic phosphate, because that presumably is how life originated. So we should be able to develop a larger scale synthetic process. But there is a catch. If we don't design the organophosphate properly, then you get publications like this. Now, organophosphates are detected in the environment. Some of them show severe toxic effects, so that it's actually an interesting idea to replace polybrominated flame retardants for organophosphates, but then obviously the organophosphates need to be fully safe, and they should not become regrettable substitutions. And so this endeavor really highlights a complex but multi-stakeholder analysis, and that's why I really like this concept. So chemistry, in my view, needs currently a triple focus. So the first is the one that we're all used to. So we focus on making molecules and materials because they have a function. We need to do this efficiently, so that's what I call green chemistry. It's not enough. So we need to add circularity, whatever cycle, durable, reusable, recyclable, to allow efficient resource use, to close the loop, to avoid waste problems. But also that is not good enough in this picture. We need to add the third focus point, where we focus on safety, so human health and environmental sustainability. And if we merge the three together, for academia it's lots of fun because the problem becomes more complex. The fundamentals are hardly known, so there is something to develop. And if you think of applicability, we need to tick the 3 boxes, and then it will make full sense. So for the organophosphates, we started with this one because it's been detected in the environment. And we thought, can we just simply randomly generate thousands and thousands of structures? And then next, most importantly, can we predict the properties using simple QSAR methods? There is a lot of room for AI and machine learning in this respect, of course. Can we focus on biodegradability, toxicity, environmental fate, and of course also the good old synthesizability. So then we selected the top 10, 20 structures, and we made them in the end. And then we also tested them against function and sustainable production. And actually this one, in terms of properties of flame retardancy, is about equal to the one on the left. That has the potential to be much more benign. So this is also, let's say, the starting point of our endeavor, which focuses on these structural motifs in a lot more detail. So the one on the top left, we identified a hazardous structural element, and we thought, can we just simply replace it with the ones that, based from our survey and analysis, came up. If you look at this target molecule, the phosphate core should come from circular production from wastewater. The ethylene, the glycol should come from the biorefinery. So you can glucose, hydrogenate, 100% atom economy to ethylene glycol. Avantium, a Dutch startup, has also been working on that. The hydroxy group is to enhance biodegradation, so that if the flame retardant enters the waterways, it can rapidly decompose, and then basically carbon, phosphorus, and so on can be taken up by the natural biochemical cycles. Then, of course, we still retain the organophosphate core as a preservation of flame retardancy function, but we now have designed it to be a bit more benign, and currently we're basically collecting all the needed data for all the different activities from ecotoxicity to flame retardancy testing and so on and so forth. So the objective here is to present a showcase and to offer a way of thinking for the design of polymer molecules and materials. So I hope to have shown you that safe and sustainable by design can be a really interesting concept, but it needs much more further development, also from academia, and then with the regulatory preparedness and the industrial relevance, we can really make a change. So with that, I'll close the loop by showing this picture again, and thank you for your kind attention.